three books that are very good, in my opinion. The first one is called Reflection Groups. And Coxeter Groups. By Humphreys, 1990. The second one is called Combinatorics of Coxeter Groups. By Bjorner and Brenty. This is from 2005. And the third one is Geometry and Topology of Coxeter Groups. By Mike Davis. And this is 2008. Okay. All right. So let me just say a quick word about the three books. There's probably a book 0 that should be on here as well, which is, maybe I'll add this at the bottom. I didn't bring my copy with me, but book 0, the original book for Coxeter Groups, is I forget exactly what it's called. I think it's Leaf Theory, chapters 4 through 7, by Bourbaki. And this is 1968. Actually, I can check in Humphreys. Just make sure I got the title right. Didn't get the title quite right. Let me give you the exact title. Actually, would you like the title in English or French? Because the original book is in French. And so the original book is called, well, Groups. It's Lie Groups and Lie Algebras. Okay. So book 0, Lie Groups and Lie Algebras, this is actually the very first time that Coxeter Groups appear in print, essentially. I mentioned Jacques Tietz as the one that invented the idea of Coxeter Groups and proved basic facts about them. He had a 1961 preprint, but I don't believe he actually ever published it. I think it stayed a preprint. And so the first time that it ever officially became in print was with Bourbaki. And if you know, do people know who Bourbaki is? Yes? No? It's an interesting story, right? It's a group of, it's not one person, it's a group of French mathematicians that decided they wanted to rewrite all of mathematics. And so they got together in the summers and they started writing new textbooks for France and for the world. And one of their later books was this book that contains a treatment of Lie Groups and Lie Algebras. Like I said, this is chapters 4 through 7. There's an earlier volume, chapters 1 through 3, that actually was published later. But this is the original place to learn about Coxeter Groups. Humphreys' book, which came out roughly 20 years later, is very good. It contains a lot of material in a very small text. And as you can tell, I've used this book a lot. For a long time, this was the main book that I had for Coxeter Groups. Lots of good information. The main thing that I would say about Humphreys' book is that Humphreys is someone who studies Lie groups and Lie algebras. And so that's his perspective. He's mostly interested in Coxeter groups as the foundation for Lie groups and Lie algebras. The two more recent books, the Combinatorics of Coxeter groups by Bjorner and Brenty, and the Geometry and Topology of Coxeter groups by Mike Davis, these are sort of third generation texts. So here's the first generation, that's the second generation. These are third generation texts, and they're more specialized. And so Bjorner and Brenty, as you might guess from the title, are combinatorialists. Coxeter groups show up in a lot of combinatorics, particularly the spherical Coxeter groups and the more general ones. And so they're mostly interested in combinatorial arguments. They're interested in doing counting, in doing bijective proofs, in connecting it up with other parts of combinatorics. And so they specialize on that portion of the theory. Mike Davis is a geometric group theorist. And so he's mostly interested in the geometry and topology. And it was sort of interesting because you might think that any book with the word Coxeter group in the title would be very similar. Mike Davis was asked to review this book in the Bulletin of the American Math Society. And one of the first things he said is that I wrote a book and they wrote a book and we have almost nothing in common. It's almost completely disjoint content. Okay? Because combinatorics, geometry, topology. The foundations are the same, but then they immediately branch off. And so depending on your interests, one or the other book might be more appropriate for you to look at. And this one is a third topic because he's focusing mostly on the foundations of Lie groups and Lie algebras. Okay? But among the three, there are many other books on Coxeter groups that are available, but these are three that I think are particularly good and have lots of good information. In particular, when I was coming to Korea and I had limited space, these are the three that I brought to make sure that I could look up things for my lectures. Okay? All right. So that I meant to do at some point. Now let me talk to you about the topic for the day. And the topic for the day is, well, we're in the third theme. We're supposed to be looking at linear representations and basic facts. We got the basic linear representation up on the board last time. But there's one thing that you might want to worry about, and that is, so what did we say? We said that if I write down some diagram with just some random numbers, then from these I can end up creating a matrix. Right? I've just put ones down the diagonal, and I put cosine pi minus pi over mij off the diagonal. And then from this, I create a symmetric bilinear form. And then from this, I look at reflections determined by the unit basis vectors. And according to the formula, R alpha of x is x minus 2 inner product of x alpha over inner product of alpha alpha alpha, which was just the formula for a reflection. If this really was dot product, this was the actual formula for reflection. Right? And what we found is that the group generated by the REIs, that there's a map from W over to the group generated by the REIs, because the REIs satisfy all the relations that the generators here satisfy. And what I claimed is that this actually is an isomorphism. That these two groups are actually the same. This is a faithful linear representation. Right? Okay, so that was a 2-minute summary of what we did last time. The thing that you might still wonder about is, and somebody did wonder about this on the course webpage, is what if we have an infinity? right? What do we have in infinity? And there's other things to worry about as well. But the main thing that I want to do today is I want to talk about what happens when you have an infinity, or more generally, what happens when you follow this procedure starting from a Euclidean Coxeter group. That when you follow this procedure with a Euclidean Coxeter group, something like 333, A2 tilde, then actually what you get over here is something that doesn't look at all like the reflecting insides of a triangle that we think it should. Okay? It's going to, yeah. So the topic for the day is understanding the representation of Euclidean Coxeter groups. I guess the standard representation. We should give it some name. Understanding the standard representation of Euclidean Coxeter groups. Okay. And so the first thing that I want to do is, what's the simplest Euclidean Coxeter group? What's the smallest one? Fewest generators. Which Euclidean Coxeter group has the fewest generators? Let's make it as tiny as possible. A1 tilde. Right? A1 tilde has the fewest generators. What does it look like? It's the diagram like that. Right? And so that's immediately leading into what do we do when we have an infinity? Okay. And this is generated by two things. Let's give them names. We'll call it A and B. So we have AB, A squared equals 1, B squared equals 1. What do we do when there's an infinity? No relation. Yeah. So we're done. Right? A squared equals 1, B squared equals 1. And what we want is that the order of AB should be infinity. That if we look at powers of AB, we should just go off forever. Right? Okay. Let's go ahead and, well, let's start with the matrix. Let's do things in order. So we're getting a 2 by 2 matrix. It's got 1s on the diagonal. And then what are we supposed to put off the diagonal? We're supposed to put cosine pi minus pi over mij. Yeah, so we've got an infinity in the denominator, so that just becomes 0. All right, so cosine pi, let's get minus 1s. All right? We just get minus 1s. What's the determinant of this matrix? 0, right? And that's actually something that's telling us that we're talking about Euclidean Coxeter groups, that we've got a nice determinant 0 matrix, but that's going to cause things to look strange when we start actually drawing these reflections. So let's go ahead and look at, so we've got E1 and E2 are two basis vectors. And what I want to do is I want to look at the hyperplanes for the two of these. So let's look at E1. So what's the hyperplane for E1? It's supposed to be all things that are perpendicular to E1, right? And what is E1 in coordinates? In coordinates, it's just 1, 0. And what do we want? So what we want, let me come over here. What we want is we want the inner product of xy and 1, 0 to be 0, right? We want the set of all points xy such that the inner product is 0. But what is this? We'll look at xy transpose matrix 1, 0, and we want that to be equal to 0, right? Let's do this since it's right here. So that's 1 and minus 1. So this is 1 minus 1, xy equals 0. And so we get x minus y equals 0, x equals y. Right? So this is the hyperplane for E1. Right? X equals y. Okay. Now we'll switch colors. And we'll do the same thing for the hyperplane for E2. It's the set of all xy such that the dot product is 0. And now when we select this, when we multiply this out, we get xy 0, 1 equals 0. Oops, sorry. We get minus 1, 1. And so we get minus x plus y equals 0. Y equals x. So what's perpendicular to this? The stuff that's perpendicular to this vector? Same line. Okay? Same line. All right. So, at this point you might think things have gone wrong, but actually we're okay. This is exactly what we were supposed to get. This is exactly the right answer. And now let's just check that this is the right answer. It's not too hard to actually check that if you write down the, oh, actually we should. Let's go ahead and write down the two transformations, RE1 and RE2. Well, let's start with visually. So what happens when I apply RE1 to this vector? It goes to there, right? What happens when I apply RE1 to this vector? Where does it go? So this is 1, 0. This is 0, 1. Where does this go? 2, 1. Why? Because if I'm doing RE1, it needs to move in this direction, and it needs to move the same distance away. Right? And since it's 1 unit away, it moves 2 units. Right? And so whatever RE1 is, it sends 1, 0 to minus 1, 0, and it sends 0, 1 to 2, 1. Right? And we can do that visually. We know that it sends this to here and it sends that to there. Right? And it's fixing these points. And in fact, once you know what it does to the basis vectors, I want to claim that we actually know what it does to an arbitrary xy. Because once you know that it does that, what's it going to do here? It's supposed to be a nice linear transformation. Right? It's going to be x of those plus y of those. Maybe I'll actually write the x's and y's on the other side. You'll see why in a second. Linear transformation, this is going to be RE1 times x plus RE1 of that times y. And so what is RE1 of this? It's going to be minus 1, 0 x plus 2, 1 y. And this will be quite immediate, but if you work backwards, you can see that this is the same as that. All right, because when you multiply this matrix times that, what you're going to get is x times that column plus y times that column. Right? Okay, so let's just record that information someplace. This is our m. I wrote it slightly too big. RE1 of xy is minus 1, 2, 0, 1 times xy. And we can either do this quite quickly, or you can just believe me that if you do the same thing, well, let's go ahead and do it. So where does RE2, what does it do to E1? If I reflect with respect to this vector, where does this go? It goes to 1, 2, right? And so that's going to give me the first column. What does it do to this vector? 0, minus 1. That gives me the second column. Okay? So these are the two matrices. And so actually, this Coxeter group, the group G, rather than thinking of it, so the group G, I can think of it as a subgroup of the general inner group of the vector space. And so in coordinates, what I'm saying is that the Coxeter group A1 tilde is isomorphic to the group generated by that matrix and that matrix. Okay? All right. We'll need those calculations a little bit later. But now let's go ahead and just see what happens if I start applying RE1, RE2, RE1, RE2, RE1, RE2, back and forth. So I'm going to start here. When I apply RE1, I go there. RE2, down there. RE1, over there. RE2, down here. RE1, back there. I just keep alternating, or if I did RE2 first, it'd be RE2, RE1, RE2, RE1. And so I go horizontal, vertical, horizontal, vertical. And because I keep switching sides, then I just keep zigzagging, and it never comes back. It has infinite order just like we wanted it to. Okay? All right. But it's a little bit different than what we had before, because what was our original way of thinking about A1 tilde? A1 tilde, we originally said, well, think about a line. Think about a one-dimensional polytope, and then look at the reflection there, and look at the reflection there. And then as you start reflecting, then you just start getting different copies of the interval. Right? This is a slightly different picture. In fact, well, it's a very different picture. Here we're actually fixing an entire line. And what does RE1, RE2 do? It ends up saying, so if I did, let's start here. If I do RE1, RE2, RE1 goes to there, RE2 goes up to here. So this point goes to there. If I do RE1, RE2 to this point goes to there, goes to there. This line stays fixed. This point goes there, goes here. This point goes there. So what's happening? Is it sort of shearing? It's fixing the line. Points on the top are moving that way. Points below are moving that way. The points further out are moving even faster. And so depending on how far away you are, but it's just shearing. Okay? All right. Which looks very different. One thing you should notice is that that the distance you are from the line is fixed. That if things that are 1 unit away from the line stay 1 unit away from the line, right? If this distance if this distance is 100, that distance is 100. That distance is 100. And so they're sort of, these things are moving, but your distances away stay constant. Okay? All right. So the main point of the lecture is going to be try to connect this picture with this picture. All right. But before I do that, I want to do a second example of the same kind of idea. And for this one, what I want to do is I want to look at, so second example. The second easiest example is A2 tilde. And so this is the diagram just with 3, 3, 3. Okay? So what's the matrix in this case? We've got 1s down the diagonal. And then off the diagonal, since they're all 3s, they're all going to be cosine pi minus pi over 3. Right? Cosine 2 pi over 3. cosine 2 pi over 3, negative a half. Right? And so negative a half, negative a half, negative a half, negative a half, negative a half. All right. Because this is a Euclidean Coxeter group, what can you tell me about the determinant? 0, right? The determinant is 0. And one thing that means, the fact that the determinant is 0 means that the columns are linearly dependent, the rows are linearly dependent. And you can actually see that if you add up if you add up all 3 rows, all 3 columns, what do you get? 0, 0, 0. And so they really are linearly dependent. Right? Okay. If we wanted to, we could go through and do exactly what we did here. We could say, let's draw the 3-dimensional picture. Let's look at RE1, RE2, RE3. We could write down explicit equations for the hyperplanes. What's going to happen is that in this case, the vector 1, 1, 1 is perpendicular to all the basis vectors. Right? Because if I put 1, 1, 1, and I just, 1, 1, 1 times that's 0, 0, 0, and then 0, 0, 0 times anything, it's going to be 0. Right? In fact, that says that this is more than perpendicular to the basis vectors. This is perpendicular to everything. Right? This is actually perpendicular every vector, which is a little bit strange, but that's what the formula tells us. Right? And in fact, anytime you've got a matrix of determinant 0, well, the fact that it's determinant 0 is going to tell you that there is going to be a non-trivial vector perpendicular to everything. Because the fact that it's determinant 0 means that its columns and rows are linearly dependent. And if you look at what happens when you take this times the first basis vector, this times the second basis vector, that's going to end up selecting out the columns. You know those images are linearly dependent. And so if you write down the dot product with E1, the dot product with E2, dot product with E3. So go ahead and take a map from V over to Rn given by x goes to x dot E1, x dot E2, just an infold list. The fact that these are linear, the fact that the columns are linearly, how do I want to say this? I want to say that because the columns are linearly dependent, then that means that this is going to be x vector times the first column, x vector times the second column, x vector times the third column. These are not going to be independent of each other. There's going to be a dependency. Because there's a dependency, this image is not the whole thing. Because this is an n-dimensional vector space, this is an n-dimensional vector space, and its image is not the whole thing, there's a kernel. Okay? And so as soon as this has 0 determinant, there is a kernel. That kernel is going to be perpendicular to all the vectors. Okay. So this is perpendicular to everything. The fact that it's perpendicular to everything means what? We're in 3-dimensional space. Here's x, here's y, here's z. Here's the vector 1, 1, 1. It's perpendicular to E1. It's perpendicular to E2. It's perpendicular to E3. What's that say about HE1, HE2, HE3? This is in HE1. This is in HE2. And this is in HE3. Right? They all contain the 1, 1, 1 vector. And so here, we had 2 hyperplanes that were actually equal. What we're going to have in this case is we're going to have a hyperplane and a hyperplane and a hyperplane that intersect along the line x equals y equals z. Okay? And so now let me change my picture so this is 1, 1, 1. Okay? So here's 1, 1, 1. So we have 3 hyperplanes. So the hyperplane for E1, the hyperplane for E2, and the hyperplane for E3 all intersecting along this line. When I start reflecting, this line doesn't move. Right? And so what happens? Well, this side moves to that side, and actually the E1, E2, and E3, since I turned my picture, are now pointing like this. And so when I reflect with E1, it moves in this direction. When I reflect with E2, it moves in this direction. When I reflect with E3, it moves in this direction. Always fixing this line. And depending on the direction, fixing a particular plane. Okay? So what's going to happen in this case, it's not going to give me the nice triangular tiling of the plane flipping in the sides. What I'm going to get instead is I'm going to get a line in 3 space that's fixed. And what's going to end up happening is that the balls of the distance from this line is going to be preserved. Okay? And so the cylinder around the line is sent to the cylinder around the line. Okay? But what will happen in one case is that if I'm looking at RE1, it'll send the cylinder to the cylinder, but it'll fix some slice and send this vector to this vector. Okay, so it's sort of flipping the cylinder and shearing it simultaneously. And then E2 will flip the cylinder and shear it. And then E3 will flip the cylinder and shear it. And when you start looking at the products, if you look at certain products, if you look at E1, E2, E1, E2, E1, E2, if you do it enough times, you'll actually get it so that it's not doing any sort of flipping or rotating. It's just doing shearing. Okay, that everything is sort of, you can take that central line and you can look at parallel copies of that line. And it's leaving the lines alone and just moving them, tipping them in different directions. Very different picture than the triangular tiling and reflecting in the sides. Okay? But it is a faithful representation. It is a faithful representation. And let's compare the two real quick. So if I have the triangular tiling, let me just draw a little bit of it. So here's my fundamental domain. And then I say, there's the flip in the first side, there's the flip in the second side, there's the flip in the third side. When I do that, there's a couple of differences between that picture and this picture. First off, this is a 2-dimensional picture. This is a 3-dimensional picture. This one is moving things around with no fixed points. This one is fixing a line. This one has a fundamental chamber that we can start moving around. But what about the normal vectors? What can you tell me about the normal vectors here? The roots. When you look at the roots, the vector perpendicular to this line, the vector perpendicular to this line, the vector perpendicular to that line, what do you see? When you see the three roots, you've got 3 roots in the plane, 3 vectors in the plane. Can they be linearly independent? No, they're linearly dependent, right? And so it turns out that what's going on here is that our hyperplanes are all nice and separate. Okay? Let's actually, so first I want to connect up this picture to this picture. And then once we have the connection, I want to do it more systematically. So first off, this is a 2-dimensional picture. This is a 3-dimensional picture. So let's fix that. How can you turn planar stuff? How can you make, so there's a common trick to turn Euclidean geometry into nice linear transformations. What you can do is you can take your 2-dimensional plane and you just put it as a plane not through the origin. Okay? So I'm going to take this 2-dimensional plane. Here's my origin. I'm going to put it up here. Okay? Now, every line in the plane, every hyperplane, I can think of reflecting. I'm fixing this line, and then I'm going to flip sides. Well, now to make it linear, to make it so it's a linear transformation, I'm going to fix the origin, and I'm fixing this line, which actually fixes this entire plane. And then I'm going to send this vector to that vector. Okay? So there's a three-dimensional reflection corresponding to this reflection. Just take that picture, put it here, put my origin down here, fix the hyperplane spanned by the origin and the line, and then use the same normal as before. And then the other line, take that line and the plane. And so what you'll end up seeing is that once I take this and I put this above my origin, is I'll see three hyperplanes through the origin, chopping out a nice fundamental cone with reflections, where my reflection vectors are all horizontal, so it stabilizes this height. And so my roots become linearly dependent, but my hyperplanes are now linearly independent. And I should say what that means in a second. But I get sort of three nice and distinct hyperplanes with no common vectors. Three nice distinct hyperplanes with no common vectors at the cost of making my roots linearly dependent. Okay? There's a similar picture over here for A1 tilde. And so what we'll do there is, well, what did we say? We said that we were thinking of it as reflections on a line. So you've got a, let me draw it at an angle just to make this easier. So here's my line. And I've got some one-dimensional polytope. And I'm thinking about the reflection there, and I'm thinking about the reflection there. Right? But now what I want to do is I want to just put my origin down below. And to make the picture pretty, I'll put it right there. So there's my origin. And so what I'll do is I'm going to fix this line and reflect that way. And then I'll fix this line and reflect that way. And so what happens is that I'll have a fundamental domain that when I apply the red reflection, then I'll get some slanted triangle. If I apply the yellow reflection, I'll get some different slanted triangle. And so what I'll get is I'll get all of my copies of my interval coned down to the origin. Right? And the line gets sent to itself, and this gets sent to there, this gets sent to there, just like we would expect. And so this picture matches the way we were thinking of it. This is the picture that we get from our representation. Okay? All right, and similarly over here, what you should be thinking is sort of a three-dimensional picture of, I don't know if I can draw this, but you've got sort of a basic triangle, and then it's sort of fixing the plane x plus y plus z equals 1, but reflecting in the xz plane, sending this plane to itself, and so it's moving in sort of that direction, or in that direction, or in that direction. So you sort of see the rough picture, right? Okay. Okay. Great. So there's actually two different linear representations of Euclidean Coxeter groups. There's the one that comes from the standard representation that we did last time, that just sort of goes through things, and we've got our M, we've got our RE1, RE2, RE3 that end up generating a group of matrices that end up working exactly, satisfying all the relations that you want, and it ends up being a nice faithful linear representation. Our second picture is to take a tiling of Euclidean space by our basic simplex, sticking it somewhere not through the origin, and then just looking at the reflections in the sides of the simplex coned off through the origin. Okay? That also ends up being a nice faithful linear representation, and because it ends up acting on this stable plane exactly like we thought, the nice geometric representation. Okay? Okay. The main thing that I want to get across to you today is that that there's just a slight switch that you can do to turn the one picture into the other picture. Okay? The two pictures are very close. They don't seem close, but they're very close. Okay? There's a nice little trick to turn this picture into this picture, to turn this picture back into that picture. Okay? And to do this, I want to talk very briefly about matrices and matrix groups. So let's look at the full group of linear transformations of a matrix. Group of invertible linear transformations of a vector space V. Okay. Actually, let me just start with an arbitrary group. And let's start with an arbitrary group, and let's start with what is a group homomorphism. It's a map, I don't know, let's call it phi, a group automorphism. A group automorphism is some nice invertible map from G to G. And what property do you want? You want it to be a group homomorphism. And so you want phi of GH to be equal to what? This is an easy question. So to be a group homomorphism, phi of GH, phi of G, phi of H, right? Okay. What about the function psi from G to G that sends a group element to its inverse? This is a nice systematic function. It does nice things. Is that a group homomorphism? Is that a group homomorphism? Is psi of GH equal to psi of G, psi of H? No, because what is this side? This side is GH inverse. And what is this side? G inverse, H inverse. And are those two the same? No, because what is this? This is H inverse, G inverse, right? It's not a group homomorphism. But it's something close that people usually don't talk about. It's what's called a, so psi is not a group homomorphism. Assuming G is non-abelian. But it is what's called a group anti-homomorphism. It's a group anti-homomorphism. What's a group anti-homomorphism? If for all G and H, psi of GH is psi of H, psi of G. That when you break apart products, you do it in the opposite order. If there's sort of a switching of left and right. Okay? If you switch left and right, and because of the way inverses work, sending an element to its inverse is an anti-homomorphism. Okay? Let's So most of the time people don't see anti-homomorphisms, but other than the fact that they look mirror image, there's no real difference. Right? It just allows you to do a few extra things, and it's nice to have a name for it because sending something to its inverse sends it to its mirror image, and it's nice to have a name for that nice function. Similarly, another case where you see this, where the order reverses, is with matrices. If you take a product of matrices and you take the transpose of the product, then what's the transpose of the product? It's the product of the transposes in the opposite order, right? And so if you think of this as actual matrices, if you give it a basis and you represent all these in matrices, there would be a map from GLV to GLV, sending every matrix to its transpose. That would be a group anti-homomorphism. Right? And so, yeah, so if you think of not just abstract vector space and the linear transformations, but a vector space with a basis, and you represent the linear transformations from that vector space to itself in that basis, so you're writing down an actual matrix, then sending that matrix represents a group element here, and sending that matrix to its transpose is a group anti-homomorphism from GLV to GLV. Okay? If I have a group and I have an anti-homomorphism and another anti-homomorphism, what happens if I compose them? I get a group homomorphism. Because this changes the direction, this changes the direction. The composition is now an honest group homomorphism. Right? Because now the order is back to the way it should be. Right? So, with matrices with an actual basis, if I take the transpose, then that's a group anti-homomorphism. If I take the matrix and I send it to its inverse, if I take every matrix and send it to its inverse, that's a group anti-homomorphism. Right? And so if I take every matrix and I send it to its inverse transpose, that's an actual group homomorphism. Right? Because taking the inverse changes the order, taking the transpose changes the order. And so doing both leaves the order alone. And so the group of all matrices, in a particular basis, and we can send M over to M inverse transpose. Defines a group homomorphism. From GLV to GLV. All right. And if you think about it for a second, it's not too hard to convince yourself that inverse transpose, transpose inverse, they actually commute with each other. That inverse is an order 2 operation, transpose is an order 2 operation, and they commute. And in particular, because they commute, I want to claim that sending M to M inverse transpose and then doing it a second time, where do you get to? You take M inverse transpose, and I'm just saying inverse and transpose commute. Then what is this? M. All right, that you get back to where you started. Convincing yourself they commute is not hard. Convincing yourself they commute is not hard. In particular, this defines a group homomorphism from here of order 2. Okay? There's a group homomorphism from there to there of order 2. And so anything of order 2 is called an involution. Right? An order 2 element is called an involution. And this is called the Cartan involution. This is called the Cartan involution. And in fact, I might need a few hypotheses, but in general, when you look at symmetries of the general linear group, if you wanted a group homomorphism from GLV to GLV, there's various things you can do. You can have it act on itself by conjugation. That ends up giving you a group homomorphism. But when you try to find unusual group homomorphisms, this is essentially it. That what's called the, for those that know what this means, the outer automorphism group of GLV is order 2, and this is it. This is the unique, unusual, non-conjugation automorphism of GLV. Okay. Let's now go back to A1 tilde. Okay. So RA1 was represented by the matrix -1, 2, 0, 1. RE2 was represented by the matrix okay. And so we said that the Coxeter group A1 tilde is actually isomorphic to the subgroup of GL2R generated by these two matrices. Okay. Maybe you see where I'm going with this now. But now we've got a subgroup of GL2R, right? And we're thinking of these as actual matrices with a particular basis. So what I want to do is I want to apply the Cartan involution to GL2R. So that's going to send GL2R to itself. And as I do that, it's going to send this matrix to some new matrix. It's going to send this matrix to some new matrix. It's going to send this subgroup to some new subgroup. But because the Cartan involution really is a group homomorphism of order 2, one thing about it being order 2, because when I do it twice I get back, that means it has no kernel whatsoever. Right? There's no kernel to this map. And so if I have a group that's isomorphic to the Coxeter group A1 tilde, its image is isomorphic to the Coxeter group A1 tilde. Right? That the subgroup can't collapse because there's no kernel to this map. And so what I want to do is I just want to apply the Cartan involution. So what does that mean? Well, I've got generators here. I just apply it to the generators. Right? And what am I supposed to do with each matrix? I'm supposed to take the matrix and I'm supposed to do the inverse transpose. Transpose is easy. Right? Just flip it over. What about inverse? What can you tell me about this matrix? What can you tell me about R? It's a reflection, which means that it times itself is trivial. It's equal to its inverse. So what's the inverse of this matrix? Itself. And you can just check that really quickly if you don't believe that. If you apply this, just to make sure that everything's going on the up and up, it really does multiply to be the identity. This is an order 2 matrix. Right? It's equal to its own inverse. And if we did all the calculations correctly, that should be true, because these are order 2 transformations. Right? It all works out. Okay, so what's the new subgroup? It's generated by, it's its own inverse, and then you transpose. And so you really just take the matrix and flip it over. And that looks like a very trivial change. Right? Looks like a very, very trivial change. And then here we flip it over. Whoops, let's try that again. Flip it over. Right? Okay. And so now, let's give these new names. Let me call this S1 and S2 just because we used R before and I don't want to confuse things. Right? So I could call it SE1, but the E's are back over here. I don't want to use E's because we're over in this new situation. So S1 of xy is now going to be minus 1, 0, 2, 1 multiplied by xy. Right? The old matrix becomes new matrix. The old matrix multiplied, the new matrix multiplies. Okay? So what I want to know is what points does S1 fix? Right? What points does it fix? What points in the xy plane does it fix? And so, well, what would that be? That would be the points. So what we want is that this is actually equal to xy. Right? Those are the points fixed by this new matrix. Well, what is that? That's the first equation. So when we multiply this, we get minus x. When we do the second one, we get 2x plus y. It should be equal to xy. And so what do we get? X equals 0 from the first equation. And once x is 0, then the second equation is fine. Right? So it's these points. So what points are fixed by S1? These points are fixed by S1. What points are fixed by S2? S2 was 1, 2, 0, minus 1, xy equals sy. And so here we get x plus 2y equals x. And we get minus y equals y. And so what do we get there? We get y equals 0. Right? And to really know what S does, we'd need to know more than what points it's fixed. We need to say, well, given some point, where does it move it? Right? Because it's not clear. We've got this general notion of reflection. So if I pick a point here, it might go there, it might go there, it might go there. It depends. Right? And so we could just take a point and figure out where it goes. But what I'd rather do is point out the following fact. And that is that if I don't want to say this. How do I want to say this? If 1, 1 times the matrix xy is k, then this product is also equal to k. And the reason is, we'll go ahead and do this multiplication first. And what do you see? When you take this times this, you're getting column sums. And the column sum here is 1, 1. And so when you multiply that, you get that. And so whatever x and y is, stays the same. Similarly, that being k, and what was the other one? 1, 2, 0, minus 1. xy equals k. And again, you multiply these two, and you see you get this. Okay, but what is this? This is some point. That's S2 of the point. This is some point. This is S1 of the point. What is 11.xy? What is that actually calculating? 11.xy equal k. Point on the line and you apply S2, you stay on the line. And we know that this is the fixed set for S1, and so S1 does this, S2 does this. And it really is our old picture. Right? This was our geometric picture. But how did we come up with this? It was nothing other than taking this picture, applying the Cartan involution of sending matrices to their inverse transpose, and then we got this picture. Okay? This picture, apply the Cartan involution, gives us this picture. I actually wanted to say a little bit more about this, and I have a little over 10 minutes, so I think I will say some of this. Part of what's going on here is that there's, let's see. Let me do a quick check of how much linear algebra you guys have seen. So from the reactions that I've been getting before, all of you have had a little bit of linear algebra. Yeah? Yes? Yes. Okay. Anytime you have a vector space, there's a dual vector space. Right? And how do you find the dual vector space? You take your vector space, let's say it's a real vector space. You look at all linear transformations from your vector space to R. And you call that a linear functional. And the collection of all linear functionals themselves form a vector space. If it's a finite dimensional real vector space, the set of all linear functionals forms a finite dimensional real vector space, same dimension. Right? Okay. Analysts like writing them as functionals. I like geometry, so I want to turn this into a picture. So how do you describe vectors? You describe vectors, one way that you often first describe vectors is that a vector is the nice rigid motion that moves this point to that point. But if you give me 2 points, the vector is from here to there. Right? But this vector is the same as this vector. It's an equivalence class of pairs of points. Right? It's an equivalence class of pairs of points. Represents a vector. And if you want a standard representation, then you take your equivalence class so that this is the origin, and then you label it by where it ends. Right? So what's a linear functional? A linear functional is a map to R. And if you wanted to describe the map to R, there's a couple of bits of information. And since I'm low on time, let me just go ahead and just jump to the answer rather than trying to motivate it. So I want to look at the kernel of the map. So you've got a map from Rn down to R. So I want to look at the kernel. That's the preimage of 0. So what is that? That's a n-1 dimensional vector space, subspace. Right? Okay? But if I just told you the kernel, that wouldn't tell you the linear functional. But I do know that if this hyperplane through the origin goes to 0, that this parallel hyperplane will all go to the same number. I just don't know which number. Right? So this one through the origin all goes to 0 means that the parallel ones have the same answer, because they differ by something in the kernel. Right? 2 points in this hyperplane differ by 2 things in the kernel. That means they give me the same answer. So if you told me, so basically, if you told me the preimage of 0 and the preimage of 1, if you gave me a hyperplane through the origin and another hyperplane parallel to it, that pair of hyperplanes determines the linear functional. right? That pair of hyperplanes determines the linear functional. And in fact, giving me an ordered pair of parallel hyperplanes anywhere in my space determines a linear functional. I can just translate so that one's through the origin, the distance is the same, and then this goes to 0, this goes to 1, that's my functional. Okay? And so I want to think of non-trivial vectors as equivalence classes of pairs of points. I want to think of dual vectors as equivalence classes of hyperplanes. Okay? When I scalar multiply a vector, I just go like this. When I scalar multiply dual vectors, I go like this. All right? And so there's a certain sense that if I just give you a line through the origin, that's a vector and all of its scalar multiples. If I just give you a hyperplane through the origin, that's a linear functional and all of its scalar multiples. Okay? And so lines through the origin are sort of the span of vectors. Hyperplanes through the origin are the span of a dual vector, if you want to actually think of them all in the original vector space. And so what's happening is, and then the connection is that if you give me a linear transformation from V to W, if you give me a linear map from a vector space V to a vector space W, and then I look at some linear, this gives me, and then I have a linear functional here, then by composing, I get a linear functional here, right? So if I have some fixed linear transformation T and I have a linear functional, then I get a linear functional, which means that I get a map from the dual space back to the dual space in the other direction. Right? That given vector space is going that way, I get linear functional. Linear transformations this way, I get a linear transformation that way just from composition. Right? If I actually picked a basis there, and I picked a basis there, this would be represented by a matrix. Bases have natural dual bases. And I could say a bit about that if I have some time, but given a basis here and a basis here, this is represented by a matrix. There's a natural dual basis, a natural dual basis. That means this has a natural representation as a matrix. This is an n-dimensional space to an m-dimensional space, I get an n by n matrix. This is an m-dimensional space to an n-dimensional space, I get an m by n matrix. If I use the original basis and the chosen bases and the dual bases, this matrix is the transpose of that matrix. And so, in some sense, the geometric meaning of transpose is that you're looking at the dual linear transformation. Okay? All right, so now to put everything together. So here, what do we have? Here, we've got a vector and a vector, which gives me a line through the origin and a line through the origin. All right, so let me actually think of the span of the vector and the span of the vector. So I've got, I'll do this one, then I'll do the higher one. So I've got a span of a vector, a span of a vector. The form, the quadratic form, is giving me a pairing between vectors and dual vectors. And so I can say, given a vector, what's perpendicular to it, and I get, so given this line through the origin, the span of a vector, I get this span of dual vectors, things parallel to this hyperplane. Okay? And what's happening is that my vectors are linearly independent, but my hyperplanes are not. What happens when you apply the Cartan involution is you apply transpose. You're dualizing the entire picture. So vectors are becoming hyperplanes. Hyperplanes are becoming vectors. And so when you apply our Cartan involution, we've got linearly independent vectors, dependent hyperplanes. Everything ends up swapping to where we have linearly independent hyperplanes, linearly dependent vectors. Same thing for A2 tilde, that we start out with three hyperplanes that are linear, the hyperplanes that all go through the line 1, 1, 1 represent dual vectors that are linearly dependent. As a hyperplane, it's dual to a vector. So we've got vectors that are linearly independent, corresponding to three hyperplanes, which I want to think of as representing spans of dual vectors. The spans of the dual vectors are linearly dependent. That's why they have a line in common. When you dualize the whole picture, the vectors become hyperplanes, the hyperplanes become vectors, and so these 3 independent vectors become 3 independent hyperplanes. The 3 linearly dependent hyperplanes become 3 linearly dependent vectors. And because you have independent hyperplanes, then you get this nice fact that once you've dualized the picture, you do chop out a nice fundamental domain that looks like a cone on a simplex. And now you can reflect. And the fact that the vectors are linearly dependent means that their span is 1 dimension less than you would expect. And parallel to that is our vectors here are going to end up being like this and like this. And parallel to their span is this hyperplane that's fixed by all the things. And that's where we're really acting. Okay. All right. So I had a little bit more to say, but I think I'm going to push that off till tomorrow. But this gives you the main idea that everything works great if both your vectors and your hyperplanes are all linearly independent. The problem comes when you've got some linear dependencies. And this trick of doing the Cartan involution is to change the dependency from the hyperplanes over into the vectors, to just swap the roles. All right, anything else that I can say that's quick? So in terms of names, different people call these different names. Sometimes this is called the standard representation, because it's the first one that was defined. It's the one that has the easiest description in terms of you've got your basis vectors and you're defining these REIs. This one is sometimes called the geometric representation, because it's the one that matches the geometric intuition in the Euclidean case. So this is the geometric representation, and this is the standard representation. But hopefully you can see now that they're really just applying the Cartan involution, and if you apply it once, you switch them. If you apply it twice, you get back. And so they're essentially the same representation. You're just replacing matrices with inverse transpose of matrices. All right. Last 2 lectures, I'm going to talk about geometric group theory and a little bit of hyperbolic geometry, and I'll save all that till tomorrow.